Alright, today we're going to be talking about implicit differentiation, and before we get into that, we should talk about what it means for a function, or not necessarily a function, an equation to be explicitly defined or implicitly defined. So, if it is, okay, so if an equation is explicitly defined, that means it can be written as y equals some function of x. So these are like your regular equations that you're used to seeing. Like y equals 5x, or y equals like 3x squared, or anything like that. These are explicitly defined functions, and when we're differentiating these, we can use our rules that we learned last time. Like if we took the derivative of y equals 3x squared, we know that would tell us that dy over dx, which just means the derivative of y with respect to x, is equal to 6x. And we all know how to do that because that's just the general power rule that we learned last time. But if we have an implicitly defined function, that's something that can't just be written as y equals a function of x. So like an example would be if you have, like in our notes, we have y squared plus xy minus x squared equals 3. We can't use this to write an equation in terms of y. So to do this, or to take the derivative of this, we have to use implicit differentiation. And this really isn't too difficult. There's just one thing we have to go over first. So if we're differentiating this term by term, so if we have like the derivative of y squared, right? You may say that that would just be 2y, but it would actually be 2y times dy over dx. Since y is a function of x, we can't like treat it as a variable and leave it how it is. And just for like an example of that, if we had like, let's say y equals or here, if we said f of x equals 3x squared plus 5 to the third, right? To differentiate this, we would first have to use the chain rule, or first the power rule and then the chain rule, because if you treat this this 3x squared plus 5 as like one function, I won't call it f of x because that's this. We have like g of x, and then if we say x cubed equals, let's say a of x, this would mean that f of x is equal to a of g of x, right? That's just plugging this function into here. And to differentiate that, that's just our definition of the chain rule. We take the derivative of the outside, leaving the inside how it is, and then multiplying by the derivative of the inside. So, for this one, the way we would do that is by first taking the derivative of the outside, which is just the power rule. So we move this 3 to the front, leave the inside how it is. So we have 3 times the quantity of 3x squared plus 5. And then we subtract 1 from this exponent, so it would be squared. And now we multiply by the derivative of the inside, which is 6x. And so this shows why we need the dy over dx when we're differentiating something like y squared, because if we set y equal to, So like in this, if we have y equals to 3x squared plus 5, right, that would make f of x equal to y cubed, right? And differentiating that, the reason why we can't just have it equal to 3y squared is because that's not equal to this up here. Because if we look at this up here, this is going to be equal to 3y squared, right? Because this inner function is your y times the derivative of y. So this is 3y squared times dy over dx, right? So we need to first treat y as a variable and then multiply by the derivative of y. So that is why whenever you're taking the derivative of y with respect to x, you can't just treat it as a variable. So like for this one, you can't just say the derivative of y squared is 2y. You have to say it is 2y times the derivative of y. Because since we don't know explicitly what y is, as this is an implicitly defined function, we just have to say this is going to be equal to 2y times the derivative of y, so 2y times dy over dx, plus, and we'll differentiate the rest of this later, or we'll just do it now. Okay, so that's really all that's like the most tricky part about implicit differentiation, is just remembering whenever you're differentiating anything which is not an x, or like a constant, you have to remember to multiply by the derivative of that, like with respect to x. And the reason why we don't do that with x, like if we have like d over dx of, again I'll just use 3x squared because we normally use that. So the reason why we don't multiply by dx over dx is because it's just that, it's dx over dx, which is just 1. Since we're differentiating with respect to x, technically we are multiplying by the derivative of x by the chain rule, but we're multiplying by 1, so we don't put that. So yeah, implicit differentiation, just anytime you see a y, write dy over dx after that term. So if we had like 2y times dy over dx for the first term, and then we have to differentiate this xy. And so to do this, we have to use a product rule, since it's the product of two things. So if you remember, if you have f of x times g of x differentiated, this is the first term times the derivative of the second term plus the derivative of the first term times the second term, right? And the shorthand is 1d2 plus 2d1. So going back to our xy up here, right? So we would do 1d2, so we would leave our x, because that is our first like term in this. So we do 1d2, and 1 is x and 2 is y, so if we're differentiating y, we're just left with dy over dx, and then plus 2d1, which is y, as that's our second, times the derivative of x, which is just 1. So the derivative of xy with respect to x is just going to be x times dy over dx plus y. And then we move on to this negative x squared, and the derivative of that is just negative 2x. Yeah, since that's just power rule. And that is equal to 0, since the derivative of a constant is 0. And whenever we're doing implicit differentiation, it's always going to ask you to solve for dy over dx. So the way to do that is get everything that's not dy over dx to one side, and then factor it out. So we have 2y dy dx plus x dy dx And then we just move these to the other side. So we get 2x minus y. And from here, we can factor out a dy over dx from this side. So factoring that out, we get dy over dx times the quantity of 2y plus x. And that's equal to 2x minus y. And then we can just divide by this to get dy over dx equals to 2x minus y over 2y plus x. And that is how you do implicit differentiation. The only tricky part about this is treating y as a constant or as a variable, like by doing the power rule for like this one, but then we also have to multiply by the derivative of y since we don't know what it is explicitly. And say if we had to find so if we had to find like all the horizontal and vertical tangencies for this function down here, for y squared plus 2x or plus xy minus x squared equals 3. So the way we would do that is, and I'm just going to write down what we found for the derivative. Y plus x, okay? So if we find all points of horizontal and vertical tangencies, so a function is going to have a horizontal tangency whenever, here I'll just write this, so horizontal tangency when derivative equals 0. And if we think about this, if we have a graph of a function, right, and it has a horizontal tangency, like right here, that means like it's tangent to the horizontal, which means the rate of change of that function is 0. Since it's going from, since it's like flattening out, it's not changing. And so that makes sense to be like the derivative is equal to 0, because the slope of this line is going to be equal to 0. And the same thing for vertical tangencies. It's going to be vertically tangent when dy over dx is undefined, right? And again, if we think about this graphically, and we have like a function with a vertical tangency, like that, the like tangent line at those points, the slope of that is going to be straight up and down, which means the like slope of that line is undefined, since we can't have like an infinite slope. So looking back here, the points of all vertical and horizontal tangencies, we just have to look at this fraction. So we know it's horizontally tangent when the derivative is equal to 0. And whenever a fraction is equal to 0, that means the numerator of that fraction is equal to 0. And so if we're finding the horizontal tangents, we have 2x minus y equals 0, since that is the numerator. And if you want, you can set this whole thing equal to 0 and like multiply by this term to both sides, and you'll just get left with this. And so if we're looking for the x values, or if we're just looking for the coordinates, we would first find the x values, so that we would get 2x equals y, and so x equals y over 2. So whenever x equals y over 2, for this function, we know that the graph of this is going to have like a horizontal tangent. And so like if so if we had, say, 4 here and then 2, we know that the graph of this would have like a horizontal tangent at this point, since x is equal to y over 2 at that point. And similarly with vertical tangencies for this one, it's going to have a vertical tangent when this is undefined, which means the denominator is 0, because we can't have a fraction with a denominator of 0. So to find this one, we would set 2y plus x, here I'll do that, 2y plus x equal to 0, and x equals negative 2y. So whenever x equals negative 2y, we know this function, I shouldn't call it function, this equation has a vertical tangency. So that is how you do implicit differentiation, and basically the hardest part about that is analyzing it and really knowing like what that means with respect to this, which is what we just did here. So we know when this equation, so when this equation is like has a horizontal tangency, we have to be able to know that that's when like the slope is equal to 0. Because like if it is horizontally tangent, then like the tangent line slope to that is 0, and that's like the definition of a derivative, which is like the slope of the tangent line. I know this can be kind of confusing, so obviously if you have questions, let me know and I'll do my best to answer them. But the main thing about implicit differentiation is just differentiate everything as normal, and then if it's not an x, multiply by dy over dx, and then solve for that. So in the next video, I'll probably get into, now that we learned this, I can show logarithmic differentiation and then exponential differentiation, which is pretty easy. And yeah, that's basically it.